When the rain began and the sky opened, the world became a single thunderous sea. Imagine a wooden box, nearly as long as a modern city block, creaking and groaning under a sky that never relented. Lightning tracked across a black horizon. Waves like moving walls rolled up against its sides. Yet that enormous craft, the Ark, did not capsize. It survived. What made it so stubbornly steady in the face of chaos? Was it only divine preservation, or did ancient design play a role? The claim we'll explore is this. Embedded in the Ark's simple description in Genesis is an engineering secret, a set of practical design principles that together would make a very large wooden vessel surprisingly seaworthy. Presented carefully, these are plausible reconstructions consistent with the biblical constraints, not archaeological certainties. But the picture they form helps us see how Noah's obedience and human skill could have worked alongside God's providence to keep that craft afloat. Genesis gives us the anchor points. In Genesis 6:15, God instructs Noah, "Make the ark 300 cubits long, 50 cubits wide, and 30 cubits high." The text names the material, gopher wood, and commands that it be pitched inside and out. Those numbers and materials limit speculation. This was a long, box-like hull with significant volume and a watertight coating. From that baseline arises a hard engineering problem. If you had to float a 300-cubit-long rectangular vessel in an ocean of storm waves, how would you stop it from rolling end over end, from bending in the middle under the weight of the sea, or from turning into a trough that simply crumples? Begin with the physics of the trouble. A floating object faces several enemies at once. Roll is the tendency to tip side to side. A tall, boxy craft with high freeboard, the distance between waterline and deck, is vulnerable. Pitch is the fore and aft rocking motion that can throw cargo and living beings into chaos. Then there is longitudinal bending. A long hull spanning troughs and crests can hog, bend upward in the middle, or sag, bend downward, when wave crests support the ends but not the center, or vice versa. Finally, even without catastrophic bending, internal sloshing, free water moving inside an open hole, can create a shifting mass that amplifies roll and pitch, turning a manageable heel into a capsize. Those are the dangers a 300 by 50 by 30 craft would face in a flood that covered mountains and churned with sudden, massive waves. We must remember what the text does and does not tell us. Scripture gives dimensions, a construction material by name, and the requirement to pitch the vessel. It does not say install bulkheads or add ballast, nor does it describe a keel or a rudder. That silence is not proof that such features didn't exist. It simply forces humility in any reconstruction.
Any engineering story we tell must remain faithful to those biblical constraints. It must be something feasible with ancient woodworking, caulking with pitch, and cargo handling by human hands. With that in mind, the engineering secret I want to propose is a three-part system, a composite set of choices that together make the Ark resilient. Call it compartmentalization, deliberate mass distribution, including ballast strategies, and an internal structural system that blends rigidity with controlled flexibility. Each part is individually sensible. Together, they form a coherent, plausible approach to stabilizing a very large wooden box at sea. First, compartmentalization. Imagine the Ark's interior not as one huge open volume, but divided into many rooms, decks and transverse partitions that break the hull into smaller chambers. Why is this so important? When water finds its way into a ship, unbroken flow across a large empty hole behaves like a liquid pendulum. A few degrees of heel allow hundreds of tons of water to rush, amplifying the tilt. But small, separated chambers turn that single swinging mass into many smaller, damped sloshes. Think of each compartment as a shock absorber. If one side takes on water, it does not flood the whole craft. The water's movement is contained, reducing the moment that would otherwise roll the vessel. Such bulkheads are a common, easily comprehensible technology for ancient ship carpentry. While Genesis does not name bulkheads, the idea is consistent with both the Ark's proportions and with known ancient practice elsewhere in antiquity. As a plausible reconstruction, partitioning preserves buoyant redundancy. If one compartment is compromised, others continue to provide flotation. Second, deliberate mass distribution and ballast. The stability of a floating body is determined not just by how much it displaces, but by where its weight sits relative to the center of buoyancy. In plain language, a low center of gravity makes a vessel much less likely to tip. The Ark's internal layout could achieve that without exotic materials.
Heavy loads, livestock, seed stores, tools for post-flood rebuilding would be stored low, on the bottom decks or even in lower compartments. Larger animals might be placed centrally and lower in the hull, with lighter cargo and living quarters above. The Bible's account implies careful loading and scheduling. Noah was to bring aboard every living thing by sevens and pairs, and to provision them. That logistical command suggests deliberate placement. Additionally, certain ballast options were available in antiquity. Stones, compacted earth, or densely packed refuse could be stored low to lower the center of gravity further. None of these requires modern technology. When you imagine that the Ark's cargo was organized like a primitive but intentional trim plan, you begin to see how much more resistant it would be to rolling.
The effect is like the ballast on a small boat, only scaled up and distributed, a stabilizing counterweight that reduces the moment caused by waves. Third, internal bracing and a hull that balances stiffness with controlled flexibility. A 300-cubit hull is a long span, subject to bending forces from waves. To resist hogging and sagging, ancient shipwrights could have used substantial longitudinal members, thick strakes and continuous beams running roughly fore and aft, combined with crossbeams and shear panels forming an internal lattice. These elements act like a spine and ribs, giving the hull stiffness where needed, while allowing the whole structure to flex slightly without breaking. In wooden construction, controlled flexibility is an advantage. A completely rigid structure might suffer brittle failure under uneven wave loads, whereas a well-braced wooden hull absorbs and distributes stress. The Ark's gopher wood and the instruction to pitch the vessel suggest an intention to create a durable, sealed timber hull. When we imagine cross-laminated planking, heavy timbers lashed and notched together, and interior frames that tie the assembly into a single load-bearing unit, the result is a craft whose parts work as a system. Cross members prevent shear, longitudinal members resist bending, and tight joinery plus pitch reduces water ingress that would otherwise compromise strength. Taken together, these three elements counter the specific dangers we named earlier. Suppose a monstrous wave strikes. The Ark's internal partitions prevent a sudden massive transfer of water that would otherwise swing the vessel into a dangerous heel. The ballast and careful stowage keep the center of gravity low, making the ship less sensitive to lateral forces. The bracing and longitudinal structure prevent catastrophic sagging or hogging by distributing loads across multiple members and allowing controlled flex. Put another way, compartmentalization limits the immediate threat of free surface effect, that swinging water problem. Mass distribution resists overturning moments. Structural reinforcement preserves the hull's integrity under longitudinal stress. This is the engineering secret, not a single miracle device, but a coordinated set of design choices that together create a resilient system. Viewed as a practical pattern, it is modest, repeatable, and consistent with a pre-industrial woodworking culture. How might this have worked in action? Picture a night when waves are tall and glassy, a rolling rhythm that could, unprepared, snap a craft in two. A wave lifts the Ark's bow onto a crest. In an unbraced, long structure, the hull between crests would be unsupported and might sag under its own weight, or the ends could be forced upward and the middle down, overstressing joints.
But if the Ark's builders placed continuous longitudinal beams under the deck and along the keel area, those beams would bridge wave troughs like a reinforced spine, transferring loads into transverse frames. Crossbeams would tie the frames into a network, so a local load doesn't become a catastrophic one. If seawater breaches one chamber, perhaps through splintered planking or a torn hatch, that chamber floods, but the adjacent compartments remain air-filled and buoyant, limiting the increase in heel. The crew can move animals, open valves, or seal hatches to rebalance the craft. Weight lower in the ship resists the roll the wave tries to impose. The net effect is damping. Oscillations are reduced in amplitude and die out rather than amplify into disaster. A key mechanical idea at play here is the suppression of the free surface effect. This is a technical phrase meaning simply that water moving unimpeded across a wide open hole multiplies instability. Smaller sealed volumes do not. Each partition shifts the dynamics from a single powerful moment to many much smaller ones that are easier to manage. Another point worth translating into everyday language: a lower center of gravity does for large ships what a tight pair of shoes does for a climber. The ship feels steadier. And finally, the internal skeleton of beams and frames distributes forces. It prevents a wave from turning one plank's failure into a chain reaction by giving the whole hull options to take load. It is tempting to look for ancient precedents that would lend weight to this reconstruction. Careful scholars note that other ancient seafaring cultures used bulkheads or internal partitions in large ships, and that Mediterranean shipwrights developed advanced caulking and joinery techniques long before modern times. These parallels do not prove the Ark used the same features, but they show feasibility.
The necessary carpentry skills and concepts were within the reach of an attentive, experienced shipbuilder. At the same time, we must be explicit about limits. The biblical text does not chronicle the ark's joinery detail. It is silent on specific structural members, keels, or ballast materials. Any claim that this proves the ark had bulkheads or stones as ballast would be overconfident. Instead, what we can say is that the three-part system, compartments, weight management, and internal bracing, is a likely reconstruction consistent with the scripture's physical parameters and with what woodworkers could accomplish in antiquity. A moment of theological balance is crucial here. Presenting an engineering reconstruction does not reduce the ark to a human invention alone. The narrative of Genesis frames the ark as an instrument of divine salvation. God commanded its construction. The text presumes divine oversight and protection. Our engineering lens simply explores how human obedience and prudence might have been expressed within that framework.
There is a complementary truth. God's providence does not make human wisdom useless. Rather, it often works through faithful, skillful action. If Noah organized his vessel with wise compartments, careful loading, and sound framing, his skillfulness would be an expression of stewardship under God's command. Likewise, if the ark's survival included miraculous preservation beyond natural resilience, that does not negate the value of sensible design. It highlights how divine action and human competence can operate together. After the reveal, if you want to dive deeper into the mechanical specifics, to see animated diagrams showing how compartment size affects slosh frequency, to watch cross-sections of how longitudinal beams might have been arranged, and to compare modeled stress distributions on a long wooden hull, there is a companion technical animation available. For viewers who love detail, that visual breakdown shows the same three-part system in motion and gives a more granular sense of numbers and movement. Click the on-screen link to watch the technical breakdown and see the plausibility of these features animated. Returning from the technical aside, consider a final, cinematic scene. The wind screams, rain hammers and beads on the pitch-black coated planks. Inside, animals are restless but contained by partitions. Their movement is damped and their weight low in the vessel. You can almost hear timbers singing as the spine shifts with a wave, then settles. A trough forms. Heavy longitudinal members bridge it, transferring load to adjacent frames. Water presses against a breached outer panel, but the pitch has sealed the joints sufficiently so that the leak is slow and the water collects in one compartment rather than rushing through the whole hull. The ark rolls and rights, rocks and rights again, sustained by a system that was simple enough to build with carpentry tools and wise enough to turn a daunting storm into a survivable test. Whether every element of this scene happened by human foresight, divine protection, or a mixture of both, the effect is the same. The craft endures. There is humility in this reconstruction. We cannot point to a fragment of ancient timber inscribed bulkhead, nor can we claim archaeological proof for these internal arrangements. The proposal remains an interpretive hypothesis, one that honors the biblical data and the plausible capabilities of ancient craftsmanship. It avoids modern anachronisms and refrains from claiming that engineering alone explains all. The real secret, if we must name it, is the harmony of practical design and faithful obedience. Noah's work in the shipyard, measured and obedient, was part of a larger story in which God preserved life. The engineering ideas we've sketched do not replace the miraculous. They illuminate how human stewardship might have been involved in the miracle. If this exploration stirred your curiosity, consider subscribing and watching the companion animation for a closer visual tour through the ark's potential interior. There you'll see the partitions, the loading plan, and how hypothetical ballast arrangements change the ship's behavior in modeled waves. Above all, let the story encourage a posture of wonder and humility. Ancient craft and divine care met in a single wooden vessel that carried life through judgment into a new world. That single combination, obedience shaping skill and skill receiving providence, is the deeper lesson the ark holds for us. The engineering secret is not merely a trick of timber and pitch. It is a reminder that human competence, exercised in reverent obedience, can be an instrument through which God shelters the fragile things He values.